Welcome to NASA's Jet Propulsion Laboratory in Southern California. Days ago, NASA's most sophisticated and capable rover to date landed on Mars, the Perseverance rover. Today, we'll see Mars like never before with new photos and videos. Our panel today will help us understand how Perseverance captured what it's like to land on Mars and what the landing site looks like. I'm your host, Raquel Villanueva, and joining us is Matt Wallace, Perseverance Deputy Project Manager, Dave Gruhl, Perseverance Entry, Descent, and Landing Camera Suite Lead, Al Chen, Perseverance Entry, Descent, and Landing Lead, Justin Mackey, Perseverance Imaging Scientist and Instrument Operations Team Chief, Jessica Samuels, Perseverance Surface Mission Manager, Ken Williford, Perseverance Deputy Project Scientist, and to tell us what this all means for NASA and exploration, Thomas Zurbuchen, Associate Administrator for NASA's Science Mission Directorate. We will take questions during this briefing. If you're a member of the media on the phone lines, press *1 to be put in the queue. If you're on social media, use the hashtag #CountdownToMars. Now, to get us started is JPL Director Mike Watkins. Now, I will step aside for him to give his opening remarks.
Thank you. Welcome back to JPL. We have a jam-packed press conference today, and I was just looking at the team here. I think we're trying to add it up, maybe 100 years of combined experience with Mars rovers on the panel today. Now, we have been working very hard since we landed. The surface team has been getting the rover set up for the surface mission. They've been working Mars time over the weekend, making fantastic progress, and you'll hear about that today. You'll also see some brand new images and videos that we acquired over the weekend, or downlinked over the weekend. And these are really fantastic images of the surface of Mars and the rest of the descent imagery that we got a preview of on Friday. These images have always been part of the history of JPL. We have taken everyone along with us on our journeys across the solar system through the rings of Saturn, looking back at the pale blue dot, and incredible panoramas on the surface of Mars. This is the first time we've been able to actually capture an event like the landing of a spacecraft on Mars. And these are pretty cool videos. And we will learn something by looking at the performance of the vehicle in these videos. But a lot of it is also to bring you along on our journey, our touchdown to Mars, and of course, our surface mission as well. And these are really amazing videos. We all binge watched them over the weekend, if you can call a 1-minute video binge watching. But we watched it many, many times, and it's really fantastic. And just to show you how far we've come in the history of JPL, I want to show one image. This is from Mariner 4 in 1965. So this was actually the first first images sent back from Mars by Mariner 4, and that was hand-colored by the engineers according to a code, kind of like a paint-by-numbers painting. And there it is, the first color image, hand-painted. And so when you see these videos later, I think Dave Gruhl and Justin Mackey will be overjoyed that they didn't have to hand-color each one of these images. So my hat is off. It's a great press conference today. My hat is off to the team, for getting the rover to where we are and these fantastic images down. And to learn more about that team, let me introduce Matt Wallace.
Thanks very much, Mike, and thanks for the nice words about the team. I'll try to be brief because I want to get to this video, and I know you do too. I just want to give you a little bit of background on how this whole thing started. My daughter is a gymnast. She's been a gymnast since she was a little kid. And when she was about, I guess, 11 years old, and the project was still in formulation, she asked me for one of those little sports cameras. And being the indulgent parent I am, I got her the sports camera, and she put it in the harness that it came with, and she put the harness on, and she did a backflip. And I don't know about you, but I cannot do a backflip. But when she showed me the video, and I watched that camera pan up to the ceiling, and then the room go upside down and then somehow right itself as she landed on her feet. You know, I felt for a moment that I had a glimpse into what it would be like if I could do a backflip. And that was the moment that inspired a phone call to my friend Dave Gruhl over here. And that's what led to this system, this entry, descent, and landing camera system. We call them the EDL cams that you're about to see the product of here just in a moment. Now, I don't know about you, but it is unlikely at this point in my career that I will pilot a spacecraft down to the surface of Mars. But when you see this imagery, I think you will feel like you are getting a glimpse into what it would be like to land successfully in Jezero crater with Perseverance. And so without any further delay, I'm going to turn it over to Dave, who'll describe the system, and we'll get to the video. Thanks.
Great. Thanks, Matt. The idea of adding a ruggedized commercial off-the-shelf hardware onto a flagship spacecraft to do a nice-to-have function proved to be quite an interesting challenge that Matt handed over to us. Along the way, we encountered one, maybe two people who were a little bit skeptical of what we were trying to do. But thankfully, we had the full support of project leadership, all the individuals directly supporting the 2020 mission were super excited to help, and in the end, we were able to actually make it happen. Our EDL CAM team were guided by two requirements, if you will. The first one was that the entry, descent, and landing system, camera system, must do no harm to the flight vehicle. And that's especially important during EDL. This was our one critical requirement, and as you all saw last Thursday, that requirement was met. The second item is not so much of a requirement as it is a mantra, if you will. We get what we get, and we don't get upset. We wanted our EDL cam system to get onto the vehicle and return amazing imagery of the vehicle landing in Jezero crater on Mars. Like every other element on the Mars 2020 spacecraft, individuals worked really hard and went above and beyond to make sure that their piece of the spacecraft did what it was supposed to do and would be successful. But in the end, we knew that our entry, descent, and landing camera system, the mission could still be 100% successful if our camera system didn't work. And if we could even get just one image or one piece of information back during EDL, that we shouldn't get upset and we should be excited. So as you probably realize after last Friday's press conference, the EDL cam system successfully captured some amazing imagery of the vehicle's descent and landing on the surface of Mars. We collected a little over 30 gigabytes of information and over 23,000 images of the vehicle descending down to the surface of Mars. As a quick introduction, if I could have the first graphic, a reminder for some of you exactly what are the sensors that we included in the entry, descent, and landing camera system. There are 3 cameras that are located on the top of the vehicle on the back shell. Those cameras actually capture high rate, 75 frames a second imagery of the parachute inflating in the Martian atmosphere. Now, one of the cameras stopped operating coincident with the mortar fire when the parachute was deployed, and that's to be expected. It is a very high dynamic environment, but luckily the other 2 cameras continued to operate as expected and captured some amazing footage of the parachutes inflating in that Martian atmosphere. We put one camera on the bottom of the descent stage. That camera looked down on the rover as we lowered the rover on the bridles. The mobility system latched into position, and then the vehicle touched down onto the surface of Mars. We also installed 2 cameras onto the rover, one on the top of the vehicle looking up on the descent stage so the rover could actually see the descent stage, lower it down to the surface, and then ideally fly off into the distance after it had delivered Perseverance safely onto the surface. And then we also put a camera on the bottom of the rover, which actually looked down on the surface of Mars once the heat shield was dropped away and that camera continued to capture imagery until the vehicle touched down on the surface of Mars. And then we also put a microphone on the port side of the rover. Now, unfortunately, I do have to say that we did not collect any audio during EDL, but please stay tuned a little bit later in this press conference because we do have some exciting information about the EDL cam microphone. So now the reaction to the EDL cam videos has been absolutely amazing around JPL. And we are super excited to actually share with all of you video imagery of Perseverance landing on the surface of Mars. Please roll the video.
Starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Alpha indicates chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
Here in safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
It gives me goosebumps every time I see it. Just amazing. I hope everybody kept their hands and arms inside the vehicle at all times while it was in motion. So I do need to say I wouldn't be sitting at this podium and you wouldn't have all seen that amazing imagery without a lot of support from an amazing team, both those who worked directly on the EDO cam task as well as those who supported us across the project. I thank you for everything you've done to get us here today. Just an amazing, amazing accomplishment. So I'm going to turn it over to Al. Al is going to be our color analyst. He doesn't have a telestrator, but he's going to actually walk through some of those videos in even more detail and actually show you some just incredible things that you can actually see once you look at those videos over and over.
I'm not sure the color commentator is supposed to have as many chills as I do right now, and every time I see these videos. But I wanted to add my thanks to the EL camera team. I mean, these videos and these images are the stuff of our dreams. It's been what we've been dreaming about for years. So thank you so much. Let's see. As Dave mentioned, we'll try to walk through what we see a little bit. We won't take that much time because we could spend literally all day looking at these videos, and some of us have spent all the weekend looking at these videos. But we'll just try to show you some highlights of what we've been seeing and invite you all to continue to look for more things as we kind of see new things every time we look at these videos. So let's start with the parachute upload camera, and let me give you a quick warning to not blink because things go really fast here. You can see that you can get a sense really of how violent that parachute deploy and inflation are. The parachute pack, the parachute is packed so densely that the pack is basically the same density as oak, and it's about 150 pounds. It gets launched out of the spacecraft with a mortar, which is basically a cannon, with a muzzle velocity of around 100 miles an hour. And the spacecraft itself was going about 1,000 miles an hour at this point, going about 1.75 times the speed of sound. So just in case you blink, let's show you that one more time. You can kind of see that in high speed and then or real time, and then we'll slow it down and take a look at the details. Okay, so let's try to walk through this a bit slower, this time at about quarter speed, and we'll pause at times to point out things we see. So let's start that rolling. Okay, here you can see the pack getting pushed out of there. You can kind of see the pack right in the middle as it's being pushed, and the parachute lid, which is right on top of it, it's kind of that circle to the left of the pack, was on top of the pack. And it was there to protect the parachute during entry. It's got some thermal protection system material on it to keep the parachute nice and cool and protected. And the pack is used to push that lid right off the vehicle, given that cannon force. You can also see some of the other things that have popped off of that lid, which is kind of expected given how violent this launch really is. So let's move on from here. So we keep going out here. You can see the pack reach what we call line stretch. So that's as far as it's going to go. It's where the parachute's going to start inflating. That's about 150 feet behind the spacecraft, and it got there in just under 1 second. So this pack is really moving. That's pretty much, as the parachute starts to come out, you can see the pack is rotated about 90 degrees. That's pretty common. We've seen that in some of our testing here on Earth at high altitude as well. So let's keep going and take a look at the inflation. So that inflation really looks textbook. It's nice and symmetric. The parachute opens in only about 7/10 of a second, again, really fast. There's no evidence of tangling of the lines, which is great. There's about 2 miles of lines in the parachute system, so the fact that we don't see any evidence of tangling or any kind of other misbehavior is great news. And I'm sure we'll be studying this video for many, many years and picking it apart frame by frame. And of course, we have a second camera on board as well that recorded this launch and inflation of the parachute. You might notice the pattern that's on the parachute here. Distinct patterns are useful in helping us determine the clocking or orientation of the parachute. Also, the contrasting sections can be useful in tracking different positions of the parachute, different portions of the parachute as it inflates. So it's especially useful when we have multiple cameras, as we do here, and are trying to track features in the parachute inflating. In addition to enabling incredible science, we hope our efforts and our engineering can inspire others. Sometimes we leave messages in our work for others to find for that purpose. So we invite you all to give it a shot and show your work. Let's move on to the Rover download camera and take a look at that in a little bit more detail. So if we start that up, you can see the heat shield falling away very nicely and symmetrically. Pausing here, we can take a look at what we see on the heat shield. First, we see the medley components on the heat shield. You can see the electronics box and the gold wires that lead to all the various sensors that measure the aerodynamics and heating during the entry portion of flight. We can also see some white flecks in different places, both on the heat shield and free flying, which are likely frost that accumulated on the heat shield. That heat shield is really, really cold during cruise, so it's not at all unexpected to see some of that frost appearing on the heat shield on the inside. You can also see something we didn't expect to see if you kind of look at the 4 o'clock position on the heat shield or so, towards the middle, somewhere between the middle and the edge. One of the springs that helped push the heat shield off seems to have come loose. It doesn't, it's not much of a big deal, but it's definitely not what we expected. If you look at the other 8 springs, they actually are where they're supposed to be, all around the edge of the heat shield. There's no danger to the spacecraft here, but it's something we didn't expect and something we wouldn't have seen if we didn't have the camera system to show us what was going on. So let's keep rolling here. we can see that the heat shield basically stays in the same orientation as it flies away from us. It'll come back into view in a little bit. But this is great. This is kind of what we expected in terms of the aerodynamics of that heat shield. It doesn't tumble or do something weird that was unexpected in flight. So that's very useful to have this video to show us that. So in the interest of time, let's skip ahead to about 15 seconds before backshell separation. So starting this video here, you can see that the spacecraft is rocking back and forth while hanging under the parachute. This rocking is less than it was earlier in flight, but pretty much what we expect. There, that white flash was backshell separation, and you can see us throttle up and begin our divert maneuver. You can see the vehicle's turned over, so we're actually beginning to fly east. And that's why you can see the delta over there. As it maneuvers eastward to the eventual landing site, it actually passes over, the field of view will pass over the landing site and then kind of overshoot it a little bit because it's got to stop that horizontal divert that we did. You can see everything's nice and smooth now that the engines are under control, that on-sheet parachute rocking is gone. So here we are, slowing down and stopping, and we're coming straight down on our eventual landing site here. You can see that as we really begin to slow down here, you can see the engines as we get lower throttle up there and stop us here. And you can see it beginning to push all that dust around on the ground on the two sides. That shaking there is the rover deploying and the mobility during a sky crane. And here we are coming down, and that rocking motion of the rover we'll see in other videos. But that settles down right before we hit the ground in a nice, safe, flat spot. There doesn't appear to be too much of concern that's right below us. So that was the rover's view looking down. Let's take a look at the descent stage view looking down as well during that sky crane portion of flight. So here we go. The rover begins to drop away from the descent stage, and that's the first part of mobility deployed. You can kind of see here right before we pause that the mobility kind of shook a little bit in that first deployment. Here you can see the bridles that are hanging down from the top of the picture. Those are what's supporting the weight of the rover below the descent stage. And if you look down toward the left, the bottom part of the image and toward the left, you can see that gold umbilical. That's what's transferring all the information between the rover and the descent stage, including this video. This picture is coming down from the camera up on the descent stage down to the rover through that cord, in addition to other information that's going back and forth. So as we keep going here, you can see the bogie deploy. That's on both sides of the mobility back. You see those wheels, the back two wheels on either side swing down. That caused a little bit of rocking of the rover as expected, but you can kind of see that kind of settles out a little bit right as we enter that plume and dust cloud as we get down and touch down. And the video ends at touchdown, of course, because the camera that's taking this video is about to leave this area in a hurry on that descent stage after we cut it loose from the rover. So now let's take a look at the rover uplook camera. So now staring up at the descent stage from the rover. So here we go. We got a really close-up look at the descent stage, and we can start rolling that. You can see the descent stage as the rover begins to fall away from it, and see the effect of that rover wobble from the mobility deploy. So pausing here, the first thing that most people will probably notice is that there's no plumes or no visible smoke or anything else coming out of the rockets at the corner of the descent stage. That's expected. Hydrazine isn't a combustion reaction when we burn it. The exhaust products are nitrogen and hydrogen, which are clear. So we expect the plumes to be clear. That's what we see in tests here on Earth as well. So I can promise you those engines are on, though. One thing you can see in the Earth testing we do is that the thrust chambers of those engines get kind of hot and glow pink. And you can kind of see that in the engines here, especially if you look at the engine at the very top right of this image. If you look closely right above the engine bell there on the thrust chamber, you can see little streaks of pink on there. And that's what's happening. As the engines have been on for a long time, they get really hot. And that heat shows up there in those pink stripes that we see. So take a look at that closely when you get a chance to look at the image in some detail. As with the previous videos, you can see the bridles that are supporting the weight of the rover there at the bottom now of this image, and that umbilical, again, transferring data back and forth between the descent stage and the rover. So let's keep going a little bit more. You'll see the image begin to wobble a little bit here. I can promise it's not the descent stage wobbling, it's actually that rover tipping back and forth a little bit as we saw as the mobility deploys, both the first initial mobility deploy and then the bogies deploying. As we near touchdown, let's slow it down a bit and proceed in slow-mo here. So now we're watching about quarter speed. Things are getting pretty dusty here as we get down toward the bottom. Take a look here at the bottom left of this picture. You'll see actually the instant that we cut the descent stage away. And you'll see those rattles begin to get retracted up toward that descent stage as they're pulled up. And this is as planned. See as they got yanked up there right before. And then we'll see the descent stage begin to turn and ascend and head out toward the northwest with the umbilical dangling behind it. Since the rover was pointed almost directly to southeast, the descent stage chose to go toward the back. That's also to make sure, of course, that the engines don't plume the rover, that we don't damage the rover with that engine thrust. So we sent that descent stage off to the northwest, which Jessica will show you about in a little bit. So I can and have watched those videos for hours and keep seeing new stuff every time. So I invite you all to do that too. So now I'll turn it over to Justin, who will talk to you a little bit about the images we've been taking on the ground.
All right, thank you, Al. I'm Justin Mackey. I'm the Mars 2020 Perseverance imaging scientist here, and I develop imaging systems at JPL. And when Dave asked me to help out with the EDL cam development about 6 years ago, I was really excited about it. I knew it would be challenging and interesting, and even possibly spectacular, but I had no idea that it would be this amazing, and we are so happy and proud, and I just want to thank Dave and Matt for just giving us the leadership and giving us the chance to do this. Like Matt and Dave and Jennifer and Rick and others on the project, I've actually worked on all 5 of the NASA rover missions, and as part of my job, I review images from Mars like every day. That's what I do. And when I saw these images come down, I have to say, I was truly amazed. And I know it's been a tough year for everybody, and we're hoping that maybe these images will, help brighten people's day. Your smartphones and make them your screen backgrounds and things. I'm just really happy that it all worked out. So now we're on Mars, and I'm going to talk a little bit about what we've been doing over the weekend. Over the weekend, we deployed the RSM, and if you go to the first picture, there's a picture of the remote sensing mast, the RSM, which is that mast on the rover, and you can see the navigation cameras up there, the left and right navigation cameras, or nav cams as we call them. This is another new imaging system that we've developed here specifically for the 2020 mission. These cameras represent a pretty significant advancement over previous imaging systems that we've flown. These are 20 megapixel color cameras with very high resolution and wide angle lenses that we use to basically map out the surface as the rover drives, and then we use these images to do planning and things. And so the first thing we did after we deployed the mast is we started imaging the surface. So the next slide shows one of our first images from the cameras. This image is actually in low resolution mode. So it's 1/4 of the full resolution of the camera, so it's been shrunk down. But you can see right there the vista that we're seeing. This is the rover, obviously, on Mars, and you can see some of the material that landed on the deck. But everything looks in good shape, and so we're using these images to inspect not only the vehicle, but the surface around us. The next slide shows the view down towards the surface. You can see the wheels there. This is the same surface you just saw in the EDL cam videos. You can see some of the scouring that the rocket plumes did for us, clean it off, make it nice and clean so we can take pictures of it and dust it off for us. The next slide shows a view looking out towards the south, and this, just an amazing scene here. This is it. This is Mars. We're here in our place that we're going to be exploring over the next months and coming years. And it's just really exciting to see. These scenes look familiar to us. They look Earth-like in a sense. You see the mountains back there and the rocks and things. It's just it really is the surface of an alien world, and we just arrived. You can also see some more scouring there over on the right. The next image looks over towards the west. You can see the delta out there in the horizon, and again more scouring from the rocket plumes. And then we take all of these images and we stitch them together into panoramas, and so that the next frame shows the full panorama from the nav cam stitched together. We're still working out the calibration and things, so this is approximate color, but it just gives you a feel for the vista here that our new environment that we're going to explore, and we're hoping everyone will join us in seeing these images. Today we're going to be releasing a whole slew of raw images. It's been a fire hose of data, basically. We have thousands of images already from the EDL cameras, nav cams. You've seen the HAZ cams. And so we will be putting those out on the website today for people to download and process yourself, or just look at the great pictures, find your favorite picture, and make it your screen background. And then the last image that I just wanted to point out is the first image, one of the first images from the Mastcam Z camera. This is another next generation imaging system on the Rover. Jim Bell's the PI. I'm the deputy PI for this, working with our industry partners, MS Cubed, down in San Diego. This is just a fantastic imaging system. This is a preview of things to come. This system has a zoom lens on it. That's what the Z stands for. And we are going to get incredibly high resolution photos from this imaging system. I just wanted to point out a few things in this picture. On the far right, you can see those cables where they had been cut in the video that you just saw. So there's kind of a close-up of that. And then just in the middle, to the left of that black instrument, that's the Rover upload camera. That's the camera that actually took the video of the sky crane as we were coming down. And then in the bottom of the frame is the Mastcam Z calibration target set. There's two of them. There's the circular one with the shadow post, and then the color chips down the bottom. There's another cal target in the back. That's the SuperCam instrument with our partners from Los Alamos and in France. We're going to be commissioning SuperCam over the next few days. And then finally, just as a teaser, I'll point out that there is a little antenna there to the right on that box, the center right. That is the helicopter antenna. It's a helicopter base station location. And preview of things to come. We're excited about that as well. So with that, I'm going to turn it over to Jessica to talk about latest status.
All right. Thank you, Justin. I know you can attest firsthand to being in the control room and the excitement that everybody has been experiencing, seeing all these images from the surface. And as they come down, we're immediately sharing them, and everybody clapping and smiles all around. So, great camera suite. So I am happy to report that Perseverance is healthy and continuing with activities as we have been planning them over the first few sols on the surface. To date, which is really only just 3 sols of activities and one more, and coming up later this afternoon, we've executed 5,000 commands. So lots of instructions to the vehicle for her to perform, and having everything come back exactly how we've been wanting it to with respect to our health checkouts and our instrument checkouts. So things have been going well. A couple key highlights. So we have fired and released our launch lock restraints to allow mechanisms to be deployed. We saw the remote sensing mast. But one of those also being the high gain antenna. Now, this is important for the high gain antenna to be deployed because it increases our uplink rate to the rover, and so it will allow us to send a higher volume of instructions to Perseverance and allow her to perform more involved activities over the days to come. Additionally, with respect to our communication, we have established a strong communication link with all of our relay orbiters and our partners, the Mars Reconnaissance Orbiter, the MAVEN Orbiter, Trace Gas Observer, the TGO, and Odyssey spacecraft. And so we thank those teams and are happy to be able to use those assets to relay all of the information that all these beautiful images that we are looking at today. The remote sensing mast motion checks were nominal and as expected, and all of our instruments have gone through their initial checkouts, and we're happy to report that they are all performing nominally and as expected. Now, when I say nominal, it really means fantastic, because we can't wait to continue to use this payload suite. Our backup computer was turned on yesterday, and that was in preparation for our upcoming flight software transition, which we will be performing over the next few days. And the Ingenuity helicopter has also been checked out, and we have performed a battery charging event, which we will continue to perform over the weeks to come in preparation for that aspect of the mission. But looking ahead, we are excited to be on our surface flight software. It is a much more surface capable, a lot more capabilities for the surface mission as part of this flight software load. It will take us a few days to transition, but once we're on that load, it will allow us to do further in-depth checkouts of the instrument, as well as deploy the robotic arm and exercise some of the turret items that you see in this image. So you can see that we have our coring drill in the center, our Pixel and Sherlock instruments mounted to the side, and that black tank is to support the gas dust removal tool, which will remove dust from the surfaces that we will be inspecting later. So coming up here, the wheels, if you noticed in the image now, are off to the side. We will be performing a wiggle. We'll straighten those up. We'll do a short drive. And as I mentioned, deploy the robotic arm, and then continue with further in-depth checkouts. So we are very excited to be happily on the surface and exercising our system and looking for what's ahead. So going back to our partnership with the larger Mars spacecraft and science teams and community, we're really excited that the MRO spacecraft, Mars Reconnaissance Orbiter, and the HiRISE team was able to find our hardware on the surface of Mars. And so if you see in this image, if the next pop-up, you can see that we have the descent stage, the parachute, and the heat shield all here in this image. With a few stats here, the descent stage is about 700 meters away from where Perseverance is on the surface. Parachute is about 1.2 kilometers, and the heat shield about 1.5 kilometers. And so it's very exciting that we can see all these different components now that we've landed on the surface. And as a special treat, the HiRISE image was able to actually acquire the entry, descent, and landing event from their perspective, and we can never have enough images of this activity, and so this is a fantastic view. But I'm going to send it back to Dave here. He, as part of this suite, we have one more surprise, or one more gift, I'll say, that we've been able to receive from this package. Over to you, Dave.
Thanks, Jessica. So I think we probably have overloaded your visual sense for a little bit. But we're going to do something a little bit different, and I'm going to have some fun here for a second, too. So I'm going to get rid of this. And I'm going to talk to you now with this. This is the microphone that was part of the EDO camera system. When the EDO cam system was first envisioned, it was set up as just a bunch of cameras to capture some amazing imagery on the surface of Mars. And about a year or so after it was first conceived, I got a phone call, another call from Matt. After talking to headquarters, asked the question, could we possibly put a microphone as part of our EDO camera system? So we worked with the team, we took a look, and sure enough, it was something that we could do. And so we started off that detailed design and identifying a microphone that would work for us and getting it onto the vehicle. About a year after this first started, I was giving a tour at JPL. And I happened to mention to the group that I was giving the tour to that the decision had come down and we were working to actually include a microphone onto the vehicle. And after the tour was done, a gal came up to me and she said some things to me that I won't forget anytime soon. She said, I'm super excited that you guys are going to try to put a microphone onto the rover and get it to the surface of Mars. And I was very appreciative. And I asked her afterwards, I said, I'm curious, why is it that this relates to you so much? And her response was that her sister was visually impaired. She was not able to see these images that we saw earlier or that we sent down in the past. And while she tries to describe them to her, she felt that she just can't quite capture that same sense of amazement that she gets when she gets them visually. And that by actually getting a microphone onto the surface of Mars, the hope was that she'd be able to experience things on Mars the same way that she was when she actually looked at them. And that stuck with me. We continued to work super hard to make sure that this microphone would work. And that's part of the reason we were disappointed why it didn't work when we actually went and did our entry, descent, and landing sequence. I wish I had actually captured that individual's name. I would love to reach out to her now and say, we've done it. I hope your sister is enjoying it. Because what I'm going to show you in a second, or what you're going to hear in a second, is actually the first sounds being recorded from the surface of Mars. So there are 2 microphones on the Perseverance vehicle. There's this microphone here, which is part of the entry, descent, and landing system, and there's a second microphone that is on the SuperCam instrument. And we're counting on both of these instruments, recording some absolutely amazing sounds from the surface of Mars. So with that, I invite you now to, if you would like to close your eyes, and just imagine yourself sitting on the surface of Mars and listening to the surroundings. If I could have the first one, please. So that gentle whirl that happens in the background, that is a noise made by the rover. But yes, what you did hear 10 seconds in was an actual wind gust on the surface of Mars, picked up by the microphone and sent back to us here on Earth. The analysis indicates that was around a 5 meter per second type of wind gust. So we can sit here now and actually tell you that we have recorded sound from the surface of Mars. So we have a second one, which basically further reduces the noise of the rover, so you can just hear what the wind would sound like on Mars. And once again, I invite you to sit back and have a listen to what it would sound like to be on Mars. It's cool. It's really neat, overwhelming, if you will. I can't remember what I was going to go and say next. So looking forward to doing some amazing things with the microphones going forward. We need to work with the ops team. There's some great science that they're looking to do. We're hopeful that we continue to use these microphones, both the SuperCam microphone and the EDLCam microphone, to capture sounds, perhaps the rocks interacting with the surface. SuperCam is going to use theirs to get some great data of them zapping rocks. So as you've heard and will continue to hear, we're just beginning to do amazing things on the surface of Mars. And now Ken is going to talk to you a little bit about the science that we've done to date and what they're looking forward to doing as we continue to move forward.
Thanks, Dave. And I'll start by just taking this opportunity to say to Matt, Dave, Al, and everybody else on this fantastic team, thank you for the ride of a lifetime. That is just incredible, what we've seen today, and what I'm sure we'll continue to see as the mission unfolds. So with all the focus on these spectacular videos and audio, we wanted to make sure to remind you that there's plenty of science going on already, with hundreds of team members poring over every new image. So if we can get the first of those images, as you'll see in this NavCam frame, we start with what may seem like very basic observations: light rocks, dark rocks, holy rocks. That's holy with an E. We use these very generic terms at this early stage until we have more data that allow us to test our hypotheses and make more confident interpretations. Follow along with the mission, and you'll see that this is a theme. As we get closer, our view of Mars continues to resolve and a coherent story emerges. Next image, please. Finally, I just want to briefly point out that we are finding real science value in these EDLCam videos. Here you can see a beautiful new perspective on the Jezero Delta. And if we can get the next image, also a new perspective on some of the beautiful stratigraphy around our landing site, which is up near on the far right side of this image. So now to put all of this in context for us, I'll hand it over to Dr. Thomas Zurbuchen.
Well, what we've seen here today is really nothing short of amazing. You know, and perhaps you've had moments like this before. Some of you have told me that I was too young to remember, but they had a moment like that, for example, when they observed the first landing on the moon. They had moments like that where it felt that we took a big leap, not just in this case because of at JPL or at NASA, but a big leap as humanity. Of course, it's a leap that was enabled by work over decades, and on this mission for close to a decade. So what's possible today, or what feels possible, is different even than yesterday. It's how it feels to make history, and that's how I feel today. I'm so moved by this. Wow. The video of Perseverance descent and landing and the amazing panorama and the first wide landscape shot of Jezero Crater seen with human eyes and the first Martian sounds are the closest you can get to landing on Mars without putting on a pressure suit. That video, I believe, should become mandatory viewing for young people who not only want to explore other worlds and build spacecraft to take them there, but also want to be part of diverse teams achieving all the audacious goals of our future. At the center of that is a team, and I'll ask for the next image. You should know, I met this team. You see me there in a dark suit next to Dr. Laurie Glaze, the Planetary Division Director, and Al, he just talked to you, is on his knee in there, and he entered the Ascend and Landing team, and we met him just hours before that historic landing. And I love this picture because, of course, the event today demonstrates that the human aspect of exploration. And that is, of course, every reason for what we can do at NASA and also why we do things. The video and audio and images here provided to us are from the surface of Mars, and sometimes we forget if we look at that. Well, Rover shouldn't get all the fun. We want to make sure that all of us on Earth see and feel what it's like to be on Mars and explore other worlds. I'm so excited for the more than 1 million students who joined the Mars Student Challenge, and the many more across the world who will be inspired by these images released today and even yesterday. Their journey is also just the beginning. Just imagine Perseverance sitting on a hill, recording the next Martian landing with a cargo that is basically a rocket, and then the first from another world with samples bound for Earth that are collected by Perseverance now in the near future. Imagine follow the entry, descent, and landing of the first human crew on the planetary surface sometimes in the future. These future historic events, which I'm confident will happen, will be enabled by women and men working in diverse teams. Imagine the goals we can achieve together. So what is possible? Sometimes to address that question, it's good to look back and think where we've come from, just like my friend Mike did earlier. We've been on a journey, both as a human race for quite a while now, and I don't want to show this next image of Sojourner, of the Pathfinder mission, which was designed for 7 sols or Martian days or so, maybe 30, ultimately lasted for 85 Earth days in 1997. I remember that really distinctly. True Pathfinder indeed, it weighed 23 pounds and returned a surprising amount of data back to Earth and a surprising amount of science for many scientists, I must say. Some people didn't expect quite that much, and that's what happens sometimes too when you innovate, just like we've seen here. We've grown from that seed. Now Perseverance is the size of a small car, and it's ready for us for the next giant leaps. And here's a picture that we're putting up that is one of the many pictures that we're releasing. And of course, it's a picture, one of my absolute favorites, and that's a picture of the sample caching system on there, because it's that sample caching system that will connect this mission to the samples that will bring back to Earth and other historic feed we're working on. This system is on the surface of Mars now. I remember distinctly looking at it before we packed it up from JPL and moved it over. Then, of course, launched it from the top of a rocket. This, my friends, is one of the indelible moments in NASA's history where what we can see and what we can learn and what we can hope for in the future and the extraordinary emotions that makes it feel all of us coming together. That human element will fuel our future at Mars, which is bright indeed. And it will fuel the dreams of a new generation that will return to Mars and also study the samples that we will eventually bring home. I'm so grateful to this team and literally the thousands, both at JPL and within the US and around the world, to all of you who have engaged in this mission. As has been noted, the raw image pipeline is opening up. Please go take a look at these data and play with them, especially those of you, the children and the youth that have signed up to our educational campaign. What can you find in these pictures? And who's going to compose the first piece of music with actual Mars sound? Mike, Matt, Jennifer, Al, many of you leaders, could not be more proud of both you and your team. On behalf of our entire NASA leadership team, a heartfelt and a proud thanks to you. For the record, Matt, I'm so glad for your idea about these cameras. We will learn a lot from that, much more than we ever expected. And of course, this is just a start. For the surface team, the real work starts now to evaluate the surrounding and start a plan and our trajectory across Jezero Crater. It's a big team and there are lots of discussions, but that's science in action. Stay with us. There is much more amazement to come. Back to you, Raquel.
Thank you, Thomas. And we'll now move on to your questions. Remember, if you are a member of the media on the phone line, you can press *1 to get into the queue. If you're on social media, you can tag questions with the hashtag Countdown to Mars. Now, starting on the phone line is Bill Harwood from CBS News.
Yeah, hi. I guess this is for Al or maybe for Matt. I mean, other than the loose spring you guys saw in the heat shield, is there anything at all in that video that looked off nominal? I mean, you know, it looked like it was almost textbook. And I'm not saying that just to, I don't know, give you free praise, but I didn't see, you know, I don't see anything like that. So is there anything? Thanks.
I can take that one. We've been poring over those videos and looking for anything that could be wrong, and also looking at the rest of the data. And we did have a pretty clean run through entry, descent, and landing. There are a couple of bits of the parachute lid that came off. Some of that was expected. In fact, we knew that there was some risk of that as well. And there was, if you look at the video, you can actually see a chunk. That's the radome. It's a cover for one of the low gain antennas we used during cruise and also during part of EDL. That came off. We had hoped that it wouldn't, and we tried to restrain it a little bit better, but we knew that it was a risk that it might. So that's something we noticed that's on there as well. There's a couple other little things that we've been taking a look at, but I think you're in general right that the entry, descent, and landing system behaved as expected, and it did what it had to do. Especially given, and a big shout out to the terrain relative navigation system, which put us down in the safest spot that was available to us. The places that we had to choose from weren't great if we didn't have something like terrain relative navigation. So yeah, the landing system worked great.
Great, thanks, Al. And up next, we have Marcia Dunn from the Associated Press.
Yes, hi. Wonderful video. I'm just wondering, did the JPL team get to see snippets coming down of the video, and then, or did you have to wait until this 1 minute video was put together? What was the reaction when you first saw the video and laid eyes on it? And for David, why do you think the mic didn't work during descent? Thank you.
I can say a couple words about the first part. I had trouble leaving this mission support area this week just because I kept waiting for every little bit of information to come back from, particularly from these cameras, but from the vehicle in general. And I can tell you, every time we got something, people were overjoyed, giddy. They were like kids, you know, in a candy store. You know, we'd get a thumbnail, which literally is just a really low-res, blobby-looking thing of one of those videos that came down first, and we'd just be falling on the floor excited with what we were seeing, and that's before even the high res came. You know, there's a lot of people that have contributed to this entry, descent, and landing system. Our chief engineer, Adam Stelzner, happens to be here in the studio. He was kind of the father of the sky crane system. This started 15 years ago for him. He and his team have never seen this system operate before, not even on the Earth, because we can't test it on the Earth. So this is the first time we've had a chance as engineers to actually see what we designed. And I just can't, it's hard for me to express just how emotional it was and how exciting it was for everybody as we got this information down. I'll turn it over to Dave to say a couple words.
Hey Dave, before you said that, can I just chime in on the first image? This is Justin. I will say, when we get these first images from any of these imaging systems, the test images never look as good as the real thing. It's not even close. In fact, it's very hard to simulate a lot of these things, especially these, sky cranes and things. And so the images that we normally see during test programs are, there's always like a ladder in the background, or the lighting's never quite right, or there's a car. In the case of the EDL cams, we have these big targets out in parking lots, and we were dodging cars to try to do our tests and things. And so that moment that you get these images from Mars, it's just kind of an electric feeling where it just all just snaps into place, and you get these pictures that are just like perfectly, they're pictures of Mars that you can never simulate here on Earth. And I think that we all experience that, especially after we go through months and months of testing, and the images don't really look that great. And people get skeptical, like, are these cameras really that great? Because that looks like a garage or something. So it's just amazing to get these pictures, and I think we all feel that way, because we're all seeing pictures of insides of labs and everything, and they're never that great. But it's amazing to get these photos from Mars. Okay. Yeah,
I'll give you my take. So Thursday evening and Friday, when the data started to come down and we kind of realized what we had, I was sitting at home, and my phone started to go off, and I was getting FaceTimes from people who were in the MSA, and what was happening was that they were starting to show them on the monitors that we have hanging on the wall, and people were turning their phones around and saying, Grul, you got to see this reaction, and people were just jumping up and down and giddy and ecstatic, and it was a great feeling. I mean, from where I was sitting, I not only was excited to see these videos that we had captured, it was also the fact that a lot of people had put in a lot of effort in to make this system work. And to actually reward that effort and to pay it back and get this excitement going, it made me super happy. I was glad to see that all the hard work, all the dedication had come in, and that everyone was just excited about not only what we had captured, but also what this mission could do going forward. So, it was a great feeling. It was a feeling I won't forget for quite some time. And then regarding the question about the microphone, we started to look at it. What we think happened is that there was a communication error between the device that is responsible for digitizing the analog signals that the microphone picked up and then passing them back to the computer that actually stores all the data. We're not exactly sure why it happened. It could have been a fact that it was just so much data streaming into the system. We tested it, but obviously everything's a little bit different on Mars than we actually have here on the ground. So we were pretty quickly able to determine we didn't think there was a hardware issue with the microphone, which is why we were able to approach the project and get their concurrence to try to turn the microphone on then on that SOL2 boundary. It's just unfortunate that error happened during the EDL, and we just weren't able to record any of the data that we generated during the sequence.
All right, thanks. And up next we have Chris Davenport from the Washington Post.
Hi, thanks for taking the time and for showing this. I really appreciate it. I wonder if you could talk a little bit about the cameras that were used to record the video. I understand they were specially designed, maybe by a commercial company called FLIR Systems. Just curious to know, like, what goes into, designing a camera to sustain the Gs, the blast of the thrusters, everything that it's got to go through to capture that images. Thanks.
Okay, so the cameras were originally purchased from a company called Point Grey, which was then bought out by FLIR. And I can tell you that the modifications we made to the camera were minimal. This was not a camera specifically designed for use on Mars. You can purchase the same camera off the internet for whatever applications you might have for it. The only things we did is we actually added some bonding material on the inside to try to make sure that in the dynamic environment of launch, and then that mortar fire event that I talked about, that the camera will continue to operate. And then we had to swap out a couple pieces on the inside because in the vacuum of space, they had the ability to outgas material, and if that material deposited itself on the detector, then we wouldn't get the clear images that we actually got. But other than that, it was not specially designed for use for this application. It is a commercial off-the-shelf camera.
Thank you. And up next, we have Michael Sheets from CNBC.
Hi, Al. Congratulations again on capturing stunning footage of this landing. I'm curious on two aspects. I mean, one, Adam Seltzer, you guys had said that in 15 years since he really engineered the sky crane, he never actually seen it in operation. I'm curious what Adam thinks about seeing this work on the planet, and secondarily, how this informs and how being able to actually see the landing informs future missions, even as NASA looks to one day land astronauts. What does this really teach you about trying to get people on the surface of Mars?
Let's see. Adam's not up here, but I can channel him for just a moment, perhaps, and tell you that this is a thrill of a lifetime. I think not just for Adam, but all the people that contributed to this architecture development back on Curiosity. I remember when we first briefed this system, with the supersonic parachutes and multi-body systems, and we're going to lower this thing on a tether, and people just looked at us like we were insane. And Adam and his team, of which Al was part, they kept at it, and they explained why it made sense. They explained why it was robust. They explained why it would work. It was not easy to build, I will tell you that, as the flight system manager on Curiosity. But once you build it and once you test it, it's something that really is designed inherently to interact with the uncertainties that Mars throws at you. And so I think being able to see his system operate like this, in high definition, landing at Jezero, it doesn't get too much better than that, I don't think. So I'm going to throw it to Al. He can maybe say a few words about the types of technologies and information that we have on the technologies on the system and information we got getting back from EDL and will be getting back as part of our reconstruction activity that feed into the future.
Yeah, I mean, I think we can talk about a lot of things. I mean, but as Matt mentioned, as a fresh-faced kid, when the sky was invented, and I was in that room, and it's amazing to see it finally in action. Even though we knew it worked once, we didn't know for sure it was going to work again, and then for it to work again, and then for us to see it is incredible. And just starting with Sky Crane there, you can see some things that I think are going to be useful to the future. One thing that's, of course, of a lot of interest, especially as we start landing bigger things, is the plume ground interaction. The interaction between those rockets and what they're doing to the ground and how they kick things around. And we've got great video of that here this time, both from the Rover download camera and the descent stage download camera. We can see how those, how they create those scours and stuff gets pushed together and creates a sheet underneath the rover. We can see that all occurring. So that's super useful. The parachute stuff too. One thing we didn't show necessarily here is that the parachute upload cameras, the two that we got, are at 75 frames per second. So we can see that inflation that only occurs in 0.7 seconds, in less than a second, and see that snap open and look at all the details of how it unfolds and how it's symmetrically inflated. And all those things are very useful for future missions, both whether they're landing more things in people or stuff and then people. SRL, other missions are going to use, future missions like the sample retrieval missions are likely going to use things like parachutes and rockets, of course. So we're very interested in seeing how those cameras and what we see in those camera images can teach us about how those systems are actually performing and make our systems more robust in the future.
Thanks, Al and Matt. Up next, we have Ken Chang from the New York Times.
Hi, thank you. I was wondering if you can give me a few more details about how the data came back. So it was 30 gigabytes that was collected. How much has come back, and what was the data rate that you were able to send them information back? Thank you.
Maybe Jessica can...
So I can say that as part of our commissioning activity, we actually walk the data rate up over the course of our different overflights with the orbiters. And so we start with a lower rate, 2,000, 8,000, and then we increase that into an adaptive data rate with the orbiter, in which we can continue to go many megabits, 2 meg, 8 meg, and then much further beyond that over the course. The total volume that I don't have off the top of my head, and so maybe, I don't know if that's something that Dave or we can provide for you later.
Justin, do you have how many images we got back?
Yeah, we counted. So we counted yesterday that we're releasing today. There was about 4,500 that we've gotten so far that we're pushing out to the web today. And I will mention that when the orbiters fly overhead, the comm passes typically return, let's say, 500 to 900 megabits per pass. And we've had, I don't know, well, we've had a lot of them now, like 5 or 10 of them.
We've typically had about 2 to 3 overflights per night, and it does vary. The rates I was referring to are the communication rates from the rover to the orbiter. And then once that's collected, then we're anywhere from, some passes will be smaller, 80 to 100, and where we've had other passes which have been significant amounts of data up at 700. And so it is variable per orbiter and per orientation.
Yeah. And I want to add one more thing I wanted to mention about the camera technology and then this data. We haven't mentioned it, but in addition to use commercial cameras, we're using a commercial computer, an Intel-based PC that's running Linux, open source. So it's the first open source, at least that I know of, open source Linux box running on the surface of Mars. It's actually inside the rover. It's quite compact. And so there's the Linux operating system. And we compress the video using FFmpeg, which is another open source tool. So thank you to the open source community for allowing us to use your amazing software. Appreciate it.
I just very briefly, I just want to note, as Jessica said, you saw some of the terrific imagery from the Mars Reconnaissance Orbiter. We've been getting fantastic support from the orbiter community, not just MRO for both that imagery and the comms, but also from Maven, which is a Goddard spacecraft, from Odyssey, one of our older orbiters, and for the ESA European Trace Gas Orbiter as well. Some of the biggest data volume passes we've had brought back a lot of this imagery came from our partners in Europe, and so thank you all to them.
Great, and up next on the phone lines is Mike Wall from space.com.
Thank you all for doing this, and yeah, it's really amazing video. Thanks for sharing it. There's a question for Dave. What do you anticipate doing maybe with the EDL mic now that it's up and running? Do you see it having any kind of diagnostic uses during the deployments of the robotic arm and sort of like the instrument checkouts and so forth? What do you see it doing aside from recording Martian wind and the sound of the dirt under the wheels and so on? Thank you.
Yes, we've had a lot of discussion about how we might be able to use both the EDL cam microphone and the super cam microphone to do those type of diagnostic stuff. I mean, the ops team right now, I don't want to speak for Jessica, but they're focused on getting the system deployed, and capturing noise of that is definitely not the first priority. They need to focus on getting this vehicle ready to perform some amazing science. But that doesn't mean in the future we could not sit down and discuss the possibility of capturing audio files of an actuator as it actually spins on the surface of Mars. The noise is an incredible thing that engineers can use to basically detect the health of moving systems, gears and actuators and things like that. And so if we get a snapshot of a actuator today, and you can compare over time, do another snapshot, another audio file of that actuator in the future, compare the two and see if there's anything that can be learned in terms of the health of that device. Now, with that said, I do need to remind everybody that the microphone that's in the EDL camera system, just like all of the cameras and other hardware, is off-the-shelf hardware. It is not designed to live in the hostile environment of Mars. It gets down 120 degrees plus below zero at night, and then it warms up significantly more in the day to, minus 40 or something like that. So those temperature cycles in that cold temperature are going to significantly limit the life of these devices. They're just not designed to last for long periods of time. The SuperCam microphone might continue to work. It actually is designed a little bit more for this particular environment. It can last longer. So I think, you know, as you heard, I think Dr. Z mentioned earlier, we're always surprised by how rugged and robust some of our items are, how long they actually last. You know, they continue to operate far longer than we designed them. We've gotten pretty lucky over the last couple of days. Perhaps we'll get lucky and the hardware will continue to operate on the surface of Mars and allow us to do those type of diagnostic things in the future. I don't know, Jess, you want to add anything more about how you might consider using them?
Well, I can say that application was one of the things that we had projected and tested and wanted to make sure that even though this was a capability that was part of the cruise and entry, descent and landing software package that we're operating right now, we've also carried that capability forward into our surface software. And so, assuming the hardware is good, we're open and ready to use it.
Yeah, and I will mention to the question, we actually have gotten requests from instrument teams wanting to turn on the microphone to observe their instrument functioning. Moxie is one of the instruments. It's going to be generating oxygen, has compressors and scroll pumps and things. And they actually want us to use the microphones to do diagnostic acoustic measurements. So I actually think that this might become something that all rovers might want, because everybody knows that when you hear something squeaking, it's diagnostic. Maybe you need to check it out, and it tells you a little bit about how it works. And so we will find out how these get used. It's actually kind of exciting, and we're getting requests from the teams. So we're working to put those into the plan.
Well, I'll just say I hope it does survive long enough so that we can hear those wheels crunch over the surface of the planet, because I think we would hear it. And I think it'd be great to hear that big rotary percussive jackhammer drill taking that first sample of a rock on Mars as well. I think we'd hear that also. So I'm hopeful that our little microphone will hang in there for some of those events.
Great. And up next is Lisa Grossman from Science News.
Hi, thanks for taking my question. The video is amazing, and a lot of it looks a lot like the animations that you've shown before the landing to kind of advertise this. Excuse me. Going forward, how will you distinguish the video that is the real video from the animations to kind of make it clear to people what they're looking at and keep them from getting confused or not be fuel for conspiracy theorists saying we haven't actually done this?
I guess I could try to take that one. I mean, I think we should label very clearly which ones are from Mars and not. I think it's clear to a lot of us, but I think you're right, given the way that the animation's been pretty good. You get a sense for how that could be confusing. I think we should label them going forward. Now that we have this kind of video, we should be clear about what's real.
What a great problem to have.
Exactly. I mean, it's an amazing problem to have.
Justin, do you have anything, any thoughts?
Yeah, I can attest to it's real. It's actually real. I know, because I know the data very well. It's stunning and it's real. And that was our thought too when we first saw it. We're like, wow, this doesn't look real, but it is, and that's what's so amazing about it. And you know, I know I've seen some of the video games are getting pretty good. You know, if second glance you look at a sports game and it looks like it's real, but it's fake. But this is actually real stuff, and that's why it's so exciting. And I actually just want to say, for those of you that want to go watch the videos, personally I like watching like quarter speed or even slower, because there's so much detail in there that anyone who's done animations knows that would take a lot of time to do, and it all happened so quickly, and the camera cut everything, and so that's how we know it's real, because we know so much about these systems, but there's just so much detail that's one way that you could look at, but yeah.
There's one other thing I forgot too. I remember early on MSL, when they started coming up with the animation for Curiosity's landing, we had a discussion about the plumes actually coming out of the descent stage, and the fact that they were clear and that you wouldn't see them in real life, like you don't see them in the Rover upload camera. But we thought that it would be that people would be expecting to see them in the animation, so they took some artistic license in putting them there. So here I can tell you now that hopefully our future animations will show the right thing and show the clear plumes like you see in the real video.
Yeah, and the same comment for the exquisite detail on the rover, if you actually look at every cal target's in place, every little twist, every tie, cable tie, they're all there. In the animations, you usually don't have that. When you get down to that level of detail, at least now you typically don't, because a lot of the things happen kind of last minute, and as the rover's getting built and people slap things on and they're not in the drawing, so the animators don't pick it up. And that's another thing that's amazing about this video. Every single detail is in there, so encourage people to look at it. It's fun.
Yeah. Thanks, Justin. It really is some beautiful detail. Now we have a social media question to take. Jerome on Twitter asks, on some pictures we can see dirt and small rocks inside the real wheel rim. Was this expected, and will it become an issue if more dust and sand is picked up along the way?
Yep, I can speak to that. So it's not uncommon for us to have rocks and dirt inside the wheels, either from the landing event or as we're driving across the surface. You'll also notice on the deck, we also experienced some of that debris coming down on top of the rover. And we design our mechanisms for these conditions, so we don't expect any issue with the material from the landing event or as we continue to rove across the surface.
Thanks, Jessica. And right now we have a call from Eric Berger on ARS Technica.
Yes, hi. Thank you very much for doing this. Congratulations on such a stunning array of photos and videos. Al Chen mentioned the dust earlier, and it was striking as the spacecraft got close to the surface how much was kicked up. It's a 1-ton rover. It's pretty sizable, but when you're talking about human missions, it's much larger. And so, what does being able to see this dust tell us about the challenge of landing future kind of much larger spacecraft on Mars? Is that something that you're going to have to account for, and if is it going to be a really significant issue to deal with? Thank you.
Yeah, I think I can take that one. I mean, I think, as most people know, right there, as far as I'm aware, there are no landing pads on Mars or barges that we can land on, prepared places. So we're going to have to deal with, especially if we're going to use propulsion, we're going to have to deal with this plume-ground interaction. And it's really difficult. It's difficult to get right, to get the modeling right, to get to understand it, or even to do a real test that shows a good impression of what you're going to come down on, especially when you don't know exactly where you're going and what the terrain is like. And what the ground properties are where you're coming down. So I do think this is a big challenge for us going forward. And that's why collecting this information here is useful. We can certainly begin to see how it actually behaved in real life and see how things began to move and what those scours are like. And then we have a vehicle that'll tell us what the ground that we happened to land on was like. And we know how we were commanding those engines and where they were pointed. So we have a rich treasure trove here of data that we can use to kind of get at that kind of challenge. Because I do think it's a big one, especially as we start to land heavier and heavier things with bigger and bigger engines.
And up next on the phone lines is Joey Roulette from The Verge.
Hey, thanks for doing this. Earlier it was mentioned that scientists are already pouring through the thousands and thousands of images, and I was just wondering what about the surface or the rocks that you guys have seen so far from these images are standing out, and kind of what has been interesting from a scientific perspective. Thanks.
Ken, Ken's there?
Yeah.
Okay, Ken.
Sure. So you can go online and see that image that was put up during my little bit there. But we're noticing basically the different colors that we see and textures and tones. And so one thing that's striking to me, standing out to me and some of us, is that a lot of the rocks that are labeled as light rocks seem to have a rough texture, whereas some of the darker rocks further afield that are higher standing, more like large boulders, seem to be smoother. That can mean something about the grain size and the potentially the composition of the rocks themselves. One of the things we're noting as the resolution gets better is that these light rocks closer to the foreground may actually be kind of dark on the inside, and that the light tone we see may be largely due to dust covering, and where the rocks stand up a bit higher and have less dust, they tend to appear dark. So a lot of new patterns are emerging. And then, of course, one of the most exciting and interesting things are these, what we call the holy rocks, that are, in some cases right under our wheels, and these smaller cobbles that are right around the rover. I didn't mention, but one of the possibilities for those holes is that they are what we would call vesicles, which would be due to gas escape from a volcanic rock. We're not calling them vesicles at this point because it's important for us to stay open to the different possible interpretations and not get locked in yet on limited data. But if they are volcanic rocks, that is enormously important to us, because it potentially provides an opportunity to get a really nice radiometric age or an absolute date if a sample like that comes back to Earth. But then again, if you go back to images from many previous Mars missions, rovers and otherwise, you'll see that wind abrasion can cause those sorts of holes in all different types of rocks. So just a few of the thoughts that are emerging, and then of course we're starting to get views of the Delta Front now, which just have us, on cloud nine, looking at some of the targets further afield that we're excited to explore.
Great. Thanks, Ken. We have another phone line question. Mark Zastro from Astronomy Magazine.
Hi, thanks for taking my question. I guess this is a question for Al, and I was just wondering if you could speak to the performance of the landing vision system, if you've gotten a chance to dive into that, how the range figure and terrain relative navigation really performed, and just sort of what it was thinking, how it was making its decisions as it descended. And then when you look at its performance and its accuracy, how do you judge it? And can you see that improvement over Curiosity?
Yeah, that'd be great. I mean, I was really hoping for a chance to speak to that a little bit, actually. The Lander's Vision System, as part of the Terrain Relative Navigation System, really did great. In fact, here's some stats, right? Based on the targeted, well, we took many images on the way down. We got tons of landmarks. We were very able to match up what we saw with our onboard map. It was almost perfect, better than many of our field tests or even simulations. So we got a very good lock on where we were. And in fact, when you combine that with our safe target selection and where we flew to, we only missed the targeted pixel by about 5 meters. So we were aiming for a particular spot on the planet once it decided what was reachable and what the safest spot was. And given how well the Lander Vision System performed and our system in flying us there, we only missed by 5 meters. So that was really great. I mean, I think we've really showed that this system can do what we wanted it to do in helping us figure out where to go and go to a safe spot.
Great. Thanks, Al. We have so many questions coming in that we are going to keep the phone lines open for a little while longer. Remember to press *1 to get in our queue. For now, I'm going to take a social media question from Bob on Twitter, who asks, how does the processing power of the onboard computer compare to a great smartphone? Matt, do you want to take that one?
Yeah, sure. That's a good question. In the space business, we have to build things that we know are gonna work. And space is a pretty hostile environment, and the surface of Mars is even worse with the temperature swings, which we were talking about. You need systems that are capable of dealing with the radiation and the temperatures and really perform with very high reliability. So as a result of that, we have a tendency to use systems that have been around for a while, that are well shaken out. And on Perseverance, we're using the same computer that we used on Curiosity, in large part because we know it worked, and we wanted to have that successful flight heritage that we had from the previous mission. So this is a computer that you would have found 15 or maybe even 20 years ago that we're flying. Having said that, these EDL cameras, which we were just talking about, are off the shelf, state-of-the-art, new technology, and it is always a thrill for us when we have the opportunity, like we did in this particular application, to bring that kind of technology into our systems. It's a very powerful way to multiply our functionality and our capability. And so this was a great example of being able to use new technology. So I don't know if that's an exact answer to the question, but in short, that's that's a summary.
Great. Thank you, Matt. And Thomas, we actually have a question for you coming in. Hayden, an 11-year-old from Ireland on Twitter asks, what advice would you give to a budding planetary scientist in working towards maybe being part of the mission that will bring back samples to Earth in the future?
Oh, I'm so glad for that question. I think about that a lot. And the advice I would give is, first of all, that's exactly the right time to get into that career. For Hayden, there could not be a better time to join that career. Even if you started 10 years earlier, or, in 10 years, now is the time to start that. The advice I would give is, go really start playing with data right away. Yes, go to school. The teachers that are there are your best allies going forward. That eventually probably you'll be perhaps at the university or at an advanced school, but go to school, do that. But the other thing I want to just give you advice on, Hayden, is we're putting all these data out. Be your own researcher. Learn how to do that. Go play with it. That's what research is so much about, and find others who are just as excited as you are. And I'm sure soon enough we'll have you on our teams in the future.
That's some great advice. Thank you, Thomas. And up next, we have on the phone lines Alexandra Witz from Nature magazine.
Great. Thanks very much. I'm not quite sure who to address this to, but I wanted to ask about InSight and whether InSight had heard Perseverance landing.
So I'm not sure anybody up here has the latest information. Do you, Al? Have you heard anything new?
Just heard from other folks on the team. I'm not sure if this is official or not, but that they hadn't seen much yet.
I think we'd have to check, to be honest, to be sure we got the right answer. So.
Great, thank you. And then another phone line question from Jackie Goddard from the Times of London.
Hello, congratulations everyone. One of the most common questions that I get from readers who aren't generally a scientific audience but regular folks is, what is the point of spending all this money to go to another planet and explore it? And sometimes that's not even a question, it's a statement. There are cynics out there. Can you say why we explore, and how does humanity benefit from you finding out what you find out and doing what you do? Thank you.
Give everyone who wants to answer time to answer.
I can, or Thomas, did you want to?
Thomas might want to comment.
Yeah, why don't I get started and turn it over to you, Matt? Is that okay if I start? Matt, you good with that?
Yeah, that'd be great.
So frankly, I'm thinking about this question all the time. Why do we explore? And of course, when we do that at NASA, I just want to let everybody know that if you look at how much money we're spending on each planet and the exploration of each planet, of course, the majority, the money the planet we're spending most money on, of course, is the Earth, the place where we live, where our friends live, where our history is, and where our future is going to be. And so we're not confused about the importance, and just as excited about the amazing future of what exploration is going forward. Exploration for us, though, is broader than just what is useful right now. And the reason we're so convinced that that is important is, first of all, the questions that have driven humanity, important questions, truly historic questions, in so many ways are what we're really about. Addressing those is what we're really about as humans. We want to be sure, as we look at our contributions of our generations, that we really move forward what we know, and also really affect how we think about ourselves. And that so often comes through research. There's a second reason, though. It's truly secondary, but I'm going to mention it anyway. So often, and surprisingly, the results and the technologies that we're building for the very questions that are really driven by fundamental science questions are extremely useful. And I just want to remind you that perhaps today, whoever asked that question is driving around in a car with a GPS system built for an entirely different purpose and looked at the weather forecast, which of course was not anticipated when in fact we built the first Earth satellite. So yes, we want to focus on the immediate needs today, and it's really important, but it's so critical for us as a species to look forward and explore? Matthew?
Thanks, Thomas. I think you said it really well. You know, I've been landing things on Mars now for 25 plus years. And so I've had a chance to go out and talk to a lot of different people. And it's not unusual when somebody asks this question. And I used to, you know, have a long list of reasons. And there are a good long list of reasons. But fundamentally, I've come to the conclusion that in some ways it's kind of a moot question, because how can we not explore? It's just who we are. It's what we are. It's in our DNA. You know, you couldn't stop us as a species from exploring, I don't think. I think it's part of the reason why we're, you know, at the top of the food chain, is because we're curious, because we want to go to places we haven't been. We want to answer questions we don't know the answer to. Sometimes we want to find the questions we don't even know need to be asked. You know, it's just part of who we are, and it opens new horizons, new frontiers. It inspires us. It inspires kids. You know, and as Thomas mentioned, all the academic programs that are paying attention here, science to technology. That we bring to the table, that's important for us, you know, and I think that's the best I can do to answer that question. There's a lot of reasons.
All right. We can move on now to another call from Matt Kaplan from Planetary Radio.
Hi, everyone. Congratulations from not just me, but all of the Planetary Society. I've been texting with our boss, Bill Nye, the science guy, who has been watching everything along with us. And here's part of his reaction. Oh, my, this is astonishing, astonishing, dare mighty things. But here's my question for Ken Williford. Ken, getting these first images and video from so much closer to the surface of Mars than we have from the orbiters, in spite of the great job that they're capable of, does this start to make you think about the potential of doing this on a regular basis from balloons or, oh, let's say, a helicopter?
Well, sure. You know, almost everything I'm thinking about right now is potential. I guess I've compared it, you know, to several people who have asked me how I'm feeling. You know, what's it like? And the closest thing I can compare it to is, I would say, the birth of my daughter, you know, where the cruise phase that's about 8 months long, you know, is like that 9-month period where you're just waiting and you're just hoping everything goes right. And then she's born. In this case, we're on the surface and it's real. And the potential is astounding. I mean, I was just, Katie Stack and I were just texting last night as we got some new images down, and we're just, you know, we're so excited, like kids, just looking at every picture and seeing so many new things and having so many new ideas and new questions are appearing. And the potential of it all is what strikes me more than anything. We have so far to go, so much to learn, and I just couldn't be more grateful to have made this transition from all the years of hard work and stress and wondering, you know, is it going to work out? How's it going to work out? To now when we actually get to do this thing, it's amazing.
Thanks, Ken. And up next, we have Irene Klotz from Aviation Week.
Thanks. Just looking ahead a bit, what's been this is probably for Jessica. Have you made any progress homing in on a site for the helicopter flight demos? And if so, about how far from the Perseverance landing site are those?
So the team has started to evaluate and is using the images that we've received from entry, descent, landing, as well as now these images that we've acquired over the last couple sols. We are fortunate to have landed in a potential spot for that, but the team is still evaluating and is looking forward to additional imaging from the 360-degree panorama from the Mastcam Z, as well as future data that's to come down. So we have not locked in a site yet. That will still be work for the team to go looking forward, whether it's here or a few hundred meters away.
And we have a social media question coming in. Jake, who is 12 years old on YouTube, asks, was there one point you thought that this would be impossible to do?
That's a great question, Jake. There might have been many points when it felt a little impossible. I'll give you my one moment, and then the other folks may want to add in. And that's last March when the COVID pandemic struck. We had just shipped the spacecraft down to Kennedy. Dave Gruhl, who, believe it or not, this whole EDL camera gig is not what he does for a living. He was our assembly, test, and launch operations manager, and he, along with his deputy Art Thompson, were responsible for assembling the flight spacecraft, testing it, and getting it down to the launch pad for launch. That's actually what he did for a day job. So the pandemic struck about a year ago, and Dave and I and Art and others were just constantly on the phone trying to figure out how to react to it and how to respond to it. I said it before, we didn't have a lot of margin, we didn't have a lot of time. We were figuring out a lot of things as quickly as we could, and our focus was shifted from trying to get the spacecraft built and tested correctly and staying on schedule for the launch, because if you miss it, you got to wait 2 years for these planetary launches to Mars. And suddenly our whole focus had to change to keeping the people safe and keeping their families safe as a #1 priority. And I wasn't sure, honestly, I wasn't sure we could do that. And I knew that if we couldn't keep them just as safe as they would be at home doing other things, that that could be it for us for this opportunity. We got tremendous support across the board from the institution here at JPL, from headquarters, Thomas and SMD, and we got through it. But that was the existential moment for me. That time right there, the first 3 to 6 weeks after COVID really hit hard. So, anybody else?
Same answer.
Yeah, exactly.
Same answers. Okay.
Yeah, I'll add to that. One of the things that's interesting about these jobs we have are we spend years. I mean, 7 or 8 years for me and all these guys. Years and years of work building, testing, making sure it's going to work. And I have to say there's some amount of stress involved when you spend 7 years of your career doing something and then it all comes down to like one moment. And for me, it's obviously like those first images that come from the cameras. Like, you really want that to work, like really, really want it to work. And you've tried everything you can do to make sure it'll work. And so, but it's definitely, we try to be open-minded about what could go wrong. We try to cover all our bases. And that's what's one of the great things about JPL is that there's a team of people here, really smart people. You go to these reviews to review your product, your designs. We call them withering reviews. You get a lot of tough questions, but that's one of the really, JPL is a real gem of a place because we built this culture of always questioning what could go wrong, but hoping for the best, and it's a really interesting experience. I think we all share that.
I will agree. I think we invite the feedback from each other and our reviewers to make sure that we are thinking about all the things that we need to think about and pushing ourselves to meet those challenges. And of course you want it all to work, but there are some things that you worry that you didn't think about. But as a community and as a collective and as a team, we use each other to help make sure that we're covering those bases.
I mean, the team really did persevere, and we are here today. Up next is Leo Enright from Irish Television.
Thanks very much, Raquel. I just realized there's no doubt about it. 12-year-olds definitely ask the best questions. But if you'll forgive me for going geeky on this, could somebody talk to the traversability of Canyon de Chelly now that you've seen these amazing pictures? Do you think that you can just simply turn around the rover and head directly west-northwest, possibly right past the descent stage? Or realistically, are you going to have to go to the northeast, around Olympic, and then to Chamanfoya? I'm sorry for being geeky, but it's kind of a serious question. Can you move quickly?
So I can, I'll comment, and I'll let Ken comment also. We have spent, as we do in our development program, as we were mentioning, a lot of time in different conditions to evaluate the performance of our system. And one of the things that we did on this mission compared to other missions was to enhance that traversability capability with enhanced autonomous navigation and as well as processing while we're driving, so to increase our drive rates. Now, we have many more images still to assess in terms of evaluating our path forward, but I'll let Ken speak to maybe some of the areas that we are interested in pursuing. And what's really great is that we work together, with the science and engineering team to evaluate those paths and what sort of terrain is the best for our system.
Yeah, so it's a great question, and it's our major focus right now on the science team is answering exactly that question. What are we going to do? What do we want to do? Where do we want to go? And I'll say, first of all, we're so extraordinarily happy about exactly where we've put down, because we ended up right on this major geologic feature, this contact, we call it, between two differently mapped units. And so you see there's this sort of undulating feature that, this sort of obvious line that we're landed right next to, and that's the big contact. One of the major features we were hoping to explore in this mission, and it presents for us one of the big mysteries. I mentioned the possible vesicles. It gets down to one of the big questions for us early on is what is that crater floor made of, and are there igneous rocks there, sedimentary rocks, both? There's a lot of implications for both. So what I would say we're probably currently leaning toward is exploring that contact, which would naturally lead us more, I think, to the second of the two options. But we'll see. We've got a good amount of time while the team does the commissioning and checks all the systems out. And during that time, we'll be digesting all those new images and doing a lot of strategic planning, evaluating different options, arguing amongst ourselves in the team. Right after this press conference is over, our first science team meeting post landing starts immediately after that. So we'll start talking about just those things. So we'll see.
Thank you, Jessica and Ken. Up next, we have Stephen Gorman from Reuters News.
Hi, thank you very much. Can you hear me okay?
Yes, we can.
Yeah. So my question is, I have a question about the superlatives regarding the video footage of the EDL sequence and the audio of that gust of wind that was picked up on the Martian service by the Microsoft. So I believe, is it correct to say this video marks the first sort of moving footage of a spacecraft from that spacecraft, showing its descent and landing on the surface of another world, Mars or any world, I think, right? I see that including the moon or an asteroid or anything. And then secondly, is this the first sound recording ever made on Mars or any celestial object other than Earth, or just the first one that was made that's been played back on Earth? I was wondering if you could just clarify that.
I can, let's see, on your first question, putting aside the Apollo program and the moon and just talking about planets, this is most certainly I'm pretty sure, as far as I know, this is the first time we've been able to see ourselves, see our spacecraft land on another planet. And hopefully that answers the question that you asked. As far as sound, I'm not sure anybody else has any more information, but again, as to the best of my knowledge, this is the first planetary sound that's been recorded. So, yeah, go ahead, Justin.
I can add to that. In terms of sound, the InSight lander has a seismometer on it, and they did measure seismic signals that were acoustically driven, and then rendered that as audio. So that could be potentially another one. But in terms of like imaging and doing video, MSL did have a descent imager that did video, 3.5 frames per second, so it was a little slower. That was the MARTI instrument. We've also done time-lapse of deployments of things on InSight. You know, we deployed a seismometer and we do time-lapse video. Mars Pathfinder, we did time-lapse video of the rover driving down onto the surface. But then again, it's time-lapse, you know, so seconds in between frames. So it, you know, you've probably seen those. They're all out on the internet. The rover movies. I worked on that as a postdoc actually, but this is definitely the best video of any of them. So I think we can at least say that pretty definitively. It's a whole nother level of capabilities that we now have. So.
Great. Well, that is all the time we have for questions today. Thank you so much to our panelists. We unfortunately can't answer all the media questions on there. For those with additional questions, please call JPL's Digital News and Media Office. Our social media team will continue to answer questions online, and we have a Reddit AMA with Perseverance team members starting at 1 p.m. Pacific time today. Now, to see the raw images of Mars, visit mars.nasa.gov/mars2020/multimedia/raw-images. For more updates on the mission, visit nasa.gov/perseverance and mars.nasa.gov/perseverance. And you can also follow us on social media using @NASAPersevere. I'm Raquel Villanueva. Thanks for watching.
Starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance has now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about 1 kilometer off the surface of Mars.
TRN Safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.